for response.
Okay, thank you. Bye.
Yeah, so this is one of the disadvantages of doing a digital workshop, because this would be ideally something to be done, say, the further offline discussion in any coffee or tea break, where we can exchange more of the details. So on the one hand, I do like the wide attendance that this web meeting allows. On the other hand, it's really a pity that these kind of discussions I have to cut short. Sorry for that. The next presentation, the last one for the break, is on an additional effect. So we look to the voltage channels so far. And one of the questions was also in normal testing of transformers in the no load loss tests with open windings where we test the core, there is a lot of effect of harmonics. And what is the effect of the harmonics on the testing? And my colleague Ye will show you our findings there. Thank you for starting, Gu. The floor is yours.
Oh, okay. Thank you, Head. I hope you can see the slide.
Yes, we can see the slides and we can hear you clearly.
Nice.
No problem.
Okay. Nice. Yeah. Good afternoon, evening, and morning. I hope I covered all the audience. I'm Gu from VSL, the Netherlands. Welcome to my presentation. In this 15 minutes, I would like to discuss the harmonic analysis during the no load loss measurement of power transformers. As we all know, if we perform the no load loss measurement of power transformers, we open circuit of one side of the transformer. So if the applied voltage is up to a certain value, the core of the transformer might be saturated. So this will lead to a significant harmonic distortion. In this study, we would like to investigate the impact of this harmonic distortion to the final measured power loss. So, second. Yes. Okay, yeah. The measurement has been done at Royal Smith, Netherlands last February, and the transformer we measured is 60 Hertz YY connection. The primary side is 380 kilovolts and the secondary is 138. There is also one auxiliary winding for only the testing purpose. So we did the measurement on this winding. The measurements are performed with 70, 80, 90, up to 115% of the rated voltage. The devices we used for the measurement is for current, we used the multi-stage current transformer, and for the voltage, the current comparator-based capacitive dividers. Also the power meter, I will go to more detail in the next slide. And the source is three-phase inverter-based. Or the power transformer itself is 600 MVA. Yeah, we're scaling down the voltage and the current, which are suitable for the measurement of the power meter. The power meter we used here is Yokogawa WT3000, and we recorded a waveform about 100 milliseconds with a sampling frequency about 10K. And if you can see the formulas in this slide, there are two formulas recommended by the IEEE and IEC standards to how to calculate the correction values of due to the harmonic distortion to the measured losses. So the P0 is actually the correct value, PM is the measured value. For the IEEE, P1 and P2 are separated, so it represents the hysteresis and eddy current losses. And we can see there's an index, K and D, actually they are same index, which describes the relation between VRMS, which is the true RMS of the voltage, and the AVG RMS, which is known as a rectified average RMS. How to calculate it? The formulas is showing the bottom of this slide. This K and D is actually an indication of how distorted the voltage is. Yeah, let's see some result. In the left part of this slide, we can see the voltage and the current waveforms during the measurements. and 100% and 115% of the nominal voltage are the example. The THD for the 100% is around 3.3% for the voltage, 48% for the current, and for the 115%, it increased dramatically, and for the THD voltage is 5.5%, and for the current, it become 88%. In the right side of the slide, I show you the calculated THD of current and voltage of the old measurement cases from 70% to 115% of the nominal voltage. And we can see the current increase from 12% to 90%, I mean the THD of the current, so it changed a lot. But for the voltage, up to 110% is always like 3.5%, but for the highest voltage level, it becomes 5.5%. Frequency spectrum. So this figure shows an example of the three-phase voltage and current frequency spectrum. We can see that the dominant voltage harmonic components appear at 3rd, 5th, 7th, 9th, and 11th. Of course, correspondingly, we can also find them in the current spectrum. We also find some ripples in the waveform here, actually. So after the Fourier analysis, we also see them from 4.5 kilohertz to 5 kilohertz, and it is confirmed by the manufacturer, and it is appear in the waveform. It's not error of the measurement, and it's related to the switching frequency of the converter. Let's zoom in to the spectrum lower than 1 kilohertz. Then we can see the distortion of 115% case. It's much more higher than the other two example, and the current is very distorted at a fifth, 3 fifths, 9, 11, etc. And because of the non-negligible output impedance, of course, we will see the distortion in the voltage as well. Yeah, next topic is about the active power and harmonic power. On the left side of the slide in the first picture, I showed the reactive average RMS voltage and the true RMS voltage, which you remember that in beginning we will use it to calculate the K and D. And then in the second picture, the active power and harmonic power are calculated. It is interesting to say that when for the highest voltage level, 115% applied voltage, then the power is -4 kilowatts. So it's about 1.6% of the total active power, but it has a negative sign. It means the transformer start to generate the harmonic power instead of absorbing. But for the cases up to 105%, all this case, the transformer is still absorbing the harmonic power. So, but the value is very low. It's around 0.1%. Oh, if we look at the harmonic power individually, which component, we see the most significant components are 5th, 7th, and followed by the 3rd. Okay, let's discuss about the accuracy of our measurement system. We have 3 components in the measurement system: voltage channel, current channel, and power meter. For the voltage channel, we use the CCB current comparator-based capacitive divider, and it is accurate within 0.01% for frequencies up to 300 Hertz, and we calibrate it in our lab. And even if we don't use this capacitive voltage divider, we use conversional VT. That previous study shows that the conversional VT is still accurate to 5% in ratio up to 1 kilohertz. Since the highest relevant harmonics we say in this measurement result is about 420 Hertz, so we think that voltage channel we still can achieve 5%. Next component is the current transformer. We think that there are no problem within 1% up to 1 kilohertz, and above 1 kilohertz, the impact is very marginal because even there are currents, there are no voltage, so there's no power. For the power meters, it's a sampling power meter, and we see that the study shows this sampling power meter can be very accurate with a deviation of most at most 0.1%, with even a very extreme distorted voltage, about 29% of the THD. So if I make a quick conclusion here that it's to measure the harmonic power losses, the accuracy can be better than 10% up to 1 kilohertz. Oh, in this slide, I calculated the IEEE and IEC correction factors with that formulas with all this waveform for the older test cases from 70% to 115%. Well, we can see the result of IEC and IEEE are very close. Secondly, the maximum correction percentage is about 1.32% for the highest voltage level, but for the lowest voltage level, the correction is less than 0.1%. Yeah, in this slide, we investigated the relation between the correction factor values and the THD. So in the first slide, in the first figure, the THD is changing from 2% to 10%, and we calculated the correction value. We found the correction value changed from 0.5% to 2.2%. And next figure shows the impact of error. So of course we have error in the measurement, considering we have measurement error about 5% in the voltage measurement, or 10% or 20%. How much is the impact? We found that with less than 5% error in the voltage THD, the maximum 1.3% correction values in the measurement will be accurate to 0.1%, so which is good news. So if it's 10%, the impact on 0.2, but it's still low. Yeah, this is the last slide of my presentation. I would like to summarize this study, that this harmonic analysis during the no load loss measurement of power transformer reach several conclusions. One, the measurement of harmonic power losses can be accurate better than 10%, up to 1 kilohertz. Secondly, the maximum correction value is about 1.3%, which for the case of 115% voltage level, rated voltage level, and for the majority of the cases when the THD is only about 3.3%, the correction value is lower than 0.1%. Considering the measurement error, if we have 5% of the measurement error in the voltage THD, the impact to the final maximum correction value will be less than 0.1%. And if it's 10% error, it doubles. Lastly, we calculated the harmonic power with the applied voltage up to 105% of the rated voltage. The transformer is still absorbing the power, harmonic power. It's about 0.1%, but up to 110% of the rated voltage, then it starts to generate harmonic power. For 110%, it's 0.3%, and for the highest value, it's about 1.6% generating. Yeah, this is my presentation, and I'm available for your remarks and questions before the coffee break. Thank you, Head.
Yeah, thank you, Gu, for this presentation. I can imagine this is not an easy subject for many of you. And I see already a question coming in, maybe on the last conclusion. Say the harmonic power is, say, at the worst case, minus 1% of the total loss power. So you have a certain loss power, and you want to measure that with a certain accuracy. So in this case, if you would measure the total loss power, say, on all frequencies, you get a certain number. But this certain number is, the total power is less than if you would just take the power at the fundamental frequency. In this case, it was a 60 Hertz transformer. So the total measured loss power was 1%, 1.6%, worst case, less than, say, the fundamental power. I see the question coming in. I'm just checking the box. Well, I do welcome, maybe you can ask your question yourself, Stefano.
Hello, can you hear me?
Hear you. Please go ahead.
First of all, thank you for your very interesting presentation. I would like to ask you, based on your experience, which is the best correction formula for the no-load losses? Because you have shown that there are some differences between IEEE and IC. So, do you think that based on your study, is it possible to improve the correction formula, or the present ones are good?
Okay, thank you for your question. Yeah, I used two formulas, IEEE and IEC. I think why the correction values are very similar in my case, the reason is although the P1 and P2 represent the hysteresis and the current losses are separate in IEEE formula, but since I don't know too much detail about that, so it's recommended in the standard, just take 0.5, so half-half. This is why they are very close. I think this is the reason. About which formulas are better, but my calculation shows that they are pretty close. And I think we need to investigate more than about that, how to improve these correction values. Yeah. Do you want to add something?
No, thank you.
I think you essentially hit the core of what I would also say. The key finding is that for the present study, the corrections indeed are very similar, although, and it's a bit empiric. So we know there's always, some limitations to the empirics of a formula. But for me, the good news is that they provide, for this particular case, very similar results. And I must say this is also due to the effect that the voltage distortion was relatively low. So it was a high voltage generator with a relatively low output impedance. In that sense, I would be curious to repeat similar measurements with a kind of a less quality generator, if you might phrase this, otherwise say a generator with a higher output impedance. I would be curious to what would be the results of the formulas on the harmonic power, and also whether the formulas would still agree that well. But from the present study, we can certainly not propose a better formula because of the simple reason they are very equal. But a very good question. Thank you, Stefano. Any other questions? I see another raised hand. I have to switch from chat to participants. I suggest it takes a while. Bengt, go ahead. I think you're still muted, Bengt, according to what I see here.
Yeah. How did you measure or how did you calculate the harmonic losses?
Once again?
How did you measure or establish the harmonic losses?
How do we calculate the harmonic losses?
Yeah.
Okay, so we recorded the waveform, both of the voltage and current, and we did a Fourier post-processing, Fourier transform, and we get the components. Then we calculate from different frequency or different order, then individually with a phase angle. Yeah, then we get.
Yeah, it's post-processing of recorded waveforms. We didn't want to rely on the instrument itself, although I think in the end the numbers were very similar, but we didn't, we did want to do our own analysis.
But how did you split out the harmonic losses? You are talking about harmonic losses compared to the total losses. How did you split it?
By looking to each individual frequency. So, for example, for the third harmonic, we have the current amplitude and phase, and the voltage amplitude and phase. And
okay, I understand. Thank you very much.
Yeah. Thank you.
And it is, of course, a very interesting showing.
Yeah.
Thank you.
Well,
thank you.
Jens, thank you for joining, and have the floor for a question. I must say this will be the last question for our break. Jens, go ahead.
Yeah, thanks, Gerd. My name is Jens Tepper from Australia University in Germany. I must say I'm a bit confused with this negative active power consumption at high harmonics. So I'm questioning myself: is it true or is it an artificial effect? And I mean, if it would be true, does it mean if I stand in a test field and I have the opportunity to produce some high-frequency harmonics, can I then reduce the measured no-load losses?
Should I or had you?
Yeah. Go ahead.
Okay. Maybe you can add something later. Supplement. Yeah. Thank you, Jens, for your question. My understanding is we have the same doubt. We had the same doubt when we were analyzing the data, but we look at the waveform and we did the Fourier transform for the voltage and current, and we look at individual orders and phase angle between them. At least from the calculation, what we saw is a negative sign, and we think it happens sometimes that the equipment will generate instead of absorb. And you are right. If it's a case that it start to generate, then it will be critical because it changes the total power thing. Then it's 1.6%. Had do you want to add? Thank you.
Well, this is exactly my answer. Spot on.
Okay, thank you. Thank you very much for the answer. It's a very interesting effect.
Yeah.
Thank
so
you.
we were really, just to add one sentence, really puzzled by this result, and we were really looking forward also to possibly extend this study, because this is just a one-off, or one transformer with one generator, one case. We would really like to see whether, say, with other, especially other generators, see whether this is really what we think it is. Yeah. Okay, we are. Thank you very much for the presentation so far, and for the very good questions. I do appreciate the questions and the discussions we had. We are slightly late, 10 minutes to be precise. We had a break planned for 20 minutes. I suggest that we make it 15 minutes. So if you can join around 3:25, around